Right, so it's my pleasure to introduce our speaker today, Tero Heikkilä. I don't know if I pronounced the name correctly, okay. Probably didn't. From the University of Jyväskylä. Okay.
Oh, that was good.
Okay, that was probably better. And thank you. And so the he is going to talk about superconductivity, which actually, if I tell you a little bit about his vita, one of the subjects he has been working most extensively since he got his PhD in what is called now Aalto University. At the time was called the Helsinki University of Technology. And actually, he was telling me that he has spent part of his time in Cazalilla, collaborating very closely with Gershon. And then after obtaining his PhD, he moved to other places for several postdoctoral stays. One of them was Basel, and yeah, other places as well. But so yeah, today, without further ado, we have him here to talk about superconductivity in graphene-based systems. And the idea is that, well, he will give a talk of 50 minutes talking about more or less earlier work, and that will be recorded, and we'll have 10 minutes of questions and answers. And after that, as it is the tradition of these seminar series, we'll have a coffee break where we can talk more informally, and that will be recorded. And he will also present some other results that he's gotten recently. Okay, so please, whenever you want. Thanks for being today online. Yeah.
Thanks, Miguel, and thank you for the kind introduction and the kind of invitation for this seminar, both to Miguel and Sebas. So this talk is going to be this 50 minutes, but don't hesitate to ask questions during the talk if there are any. So I'm happy to answer them. We just discussed that this is now the third time that I'm giving a talk on something related with this topic in San Sebastian. Unfortunately, now I'm not physically there, but maybe hopefully in the near future that will be possible. And I also hope that my slides have changed a bit since the previous talks. So what you see here is Jyväskylä, and I'm actually in this building here at the moment. This is the center of Jyväskylä, and if you go from the center to our Nanoscience center, you have to cross this bridge, which is very nice actually, because it's a pedestrian bridge. You can the view changes every day depending on weather on the lake. Yeah, so I will tell about work that we have done actually in the past 10 years related with the sort of description of superconductivity in different types of graphene-based systems. And now, actually, nowadays there are lots of experiments that also connect with that work. Let's see. The work has been done together with many people. We started especially with Grisha Volavik in Aalto University, and also with the late Nikolai Kopnin to study the superconducting state. And then many of the more recent works have been done together with 3 different students, Teemu Peltonen and Risto Ejärvi from Jyväskylä, and Aleksi Julku, who was a student of Päivi Törmä in Aalto University. And also Timo Hyart contributed at times a lot. Yes, and actually Teemu Peltonen finished his PhD a bit more than a year ago, and contains a lot of details related to what I'm talking about here. Aleksi also actually finished his thesis just before the pandemic, and Risto is now finishing his PhD thesis. So those theses contain sort of many of the details of what I'm talking about here. What I will try to tell you about is sort of what is the notion of flat bands, how it is connected with superconductivity. And then I will give you a few examples where we go towards the flat bands. and these are now sort of experimentally relevant. And in fact, we wanted to sort of study these systems together with experimentalists, including some from Madrid. And we made a proposal 2015 to study systems where we would have studied superconductivity in ABC graphene, in sort of periodically strained graphene, and in twisted bilayer graphene. But unfortunately, we didn't get the funding. But now I can show with this next slide that sort of majority of these systems have been actually realized recently in the USA in different groups, and showing sort of superconductivity in graphene-based systems. You may have seen this picture here. It is from Pablo Herrero's group, who found superconductivity in twisted bilayer graphene. I will sort of discuss a model for the superconductivity during my talk. But there are also two recent papers from Andrea Young's group from Santa Barbara, where they found superconductivity in rhombohedral relay graphene, and now very recently also in Bernal bilayer graphene. And then sort of this periodically strained graphene has been realized in Eva Andres' group in Rutgers, and they indeed find flat bands in those systems and also some correlation effects in STM experiments, but they cannot tell whether these become superconducting or not. I believe they are not, those samples are probably not yet superconducting. Okay, let me start with something sort of very generic, which is that of sort of classifying different types of non-interacting electron spectra. So let's say we could make now kind of three different classes of spectra. So those of band insulators, which typically tend to be pretty boring in many respects. Those of metals, where the physics is dominated by what happens at the Fermi surface. So let's say the low energy physics is dominated by that. And then we can have semi-metals, which have these band crossings, and they are especially interesting sort of once they are doped close to this band crossing point. If they are doped sort of away from the band crossing point, typically the low energy physics is that of Fermi surface physics again. So this kind of goes back to this second example. So these are kind of general classes of electronic spectra, and of course the real materials are in principle much more complicated, but the concepts that we use to describe them are based on these simple pictures. Of course, as an example of such a semi-metal where you have this band crossing, I believe you all know graphene, which consists of this hexagonal structure of sort of carbon atoms, where the electronic sort of structure, electronic spectrum contains this sort of pairs of valleys where you have the Dirac crossing of the spectra. And yeah, so you can actually extend this by going to bilayer graphene. If you stack two graphene sheets on top of each other, this Dirac crossing goes to this quadratic touching point. I will discuss it a bit more in the future, later in my talk. But now you can start from this bilayer graphene and from the quadratic crossing, and if you increase the number of layers in a suitable way, you actually get sort of higher order sort of dispersion. And in this rhomboidal multilayer, you get sort of in principle sort of nth order dispersions, which for large n go towards a flat band. So this is kind of one way to get to a flat dispersion. Another way that I will discuss a bit in my talk is to get to a flat band is to take this graphene dispersion and simply sort of lower the speed. Okay, this is actually what happens in twisted bilayer graphene and also in this periodically strained graphene. So, and what you see from this picture here is that sort of whether we are here or here depends on what we actually, in which scale we plot the energy, right? So this basically just tells that if we talk about flat bands, the relative flatness depends on a reference scale to which we are comparing this sort of band structure. And I will show how this reference scale is relevant for superconductivity, which reference scale is relevant. So actually, this means that I will have to extend my classification. So from these band insulators, sort of metals and semi-metals, to the case of flat bands. And this would be an ideal flat band, which probably it's an idealization that doesn't really take place in practice. You will always have some finite bandwidth that you then need to compare to other quantities of interest. So here is, for example, the flat band in twisted bilayer graphene as a function of momentum. Okay, so that's kind of the non-interacting spectrum. But we know from in say quantum mechanics 2 is that this is only sort of one part of the story. So what you really need to do is to actually add interactions. So basically the way how you do it is that you write on top of this one body spectrum, you write the two body interactions, and then you may ask the question of how to characterize the ground state of this interacting problem. And well, you have the many body problem that actually it turns out to be impossible to characterize the exact ground state in a large N system, but you can always make some approximative schemes. And the most commonly used approach to this is the Hartree-Fock mean field theory. And typically, actually, sort of for models that I described here, you even go to you kind of make an idealized description of this interaction. So often some local interaction is considered. In this case, you have your ground state is actually a Fermi gas of a suitably defined operator. So that you need to sort of transform this operator to a new one, and then you have a non-interacting system. And but typically these ground states then sort of they lead to these mean fields and spontaneous symmetry breaking. And one of the sort of well-known mean fields is that of the superconducting state, or the BCS mean field. The superconducting state has a broken symmetry, and it is described by this order parameter, which is the pairing amplitude F, where you take the product of two annihilation operators, and you take the expectation value over the basically the mean field state of the system. And if this becomes finite, you have a superconducting state. And why it's superconducting is the fact that this quantity is a complex number, and so it has an amplitude and a phase, and there is a supercurrent associated with the phase gradient. And the prefactor of this supercurrent is called superfluid weight, and I will discuss this superfluid weight later in my talk. Superconductors, of course, have several characteristic properties, such as the zero resistance or vanishing resistivity. They actually have a large inductance as well. They have the Meissner effect. They have a gapped spectrum. Often in small systems, they may have the parity effect and so on. In fact, all the systems that I study here, all the experimental systems, they are characterized by this vanishing resistivity. And then the question is, experimentalist, how do you measure zero in resistance? But basically, there are pretty good arguments anyway that the resistivity here goes to zero in those systems. Okay, so how do you get to this finite order parameter. Basically, what BCS, Baring-Cooper-Schiffer, and Cooper, especially Cooper, showed is this Cooper instability, that if you have an arbitrarily weak attractive interaction between electrons, this leads to superconducting state at 0 temperature. And then Pardeen, Miguel, and Eliasberg and others showed how this attractive interaction arises from electron-phonon coupling, at least. There are also other mechanisms for it, but this is the best known one. And so at least for conventional superconductivity, this is the relevant mechanism. And also in the BCS limit, what one usually assumes that this interaction, even though it's mediated by phonons, it is assumed that this interaction is almost instantaneous. Okay, and so one way to then do the mean field is that you sort of study what happens due to this sort of emergence of this order parameter. And one thing that you find out is that typical cases is that you have a gapped dispersion. This dispersion, this gap may depend on momentum, but here I just consider the S-wave case where it doesn't depend on momentum. And you can actually write the free energy of the superconducting state as a function of this pairing potential, and containing the condensation energy and then the change in the quasi-particle kinetic energy. And the mean field delta is actually obtained by just considering the minimum of this free energy. And once you do this, you get this so-called self-consistency equation. So which relates the gap to itself and the spectrum, energy spectrum. So this way you can then study how the energy spectrum affects the gap in these systems. Okay. There are a few sort of generic limits where you can do this. So the most common one is this Fermi surface case, and the best known one, where there is a logarithmic divergence in the BCS gap equation, and you need to cut it off somehow, and as a result of this cutoff, you get actually an exponentially suppressed delta. And this is the form of the BCS sort of delta versus the coupling strength G, where the prefactor here is the cutoff energy, which is either for electron phonon, it's typically considered to be dBi energy, but for sort of flat bands, it could also be just a bandwidth in here. But the bottom line is that you have an exponentially suppressed sort of energy scale compared to the microscopic energy scales in this system. Now you can consider the case of graphene, which has a linear dispersion. So, and especially, let's say, 2D case. And what one finds just by plugging in this dispersion to the mean field, this self-consistency equation, is that actually the delta becomes even smaller. So there is actually this Cooper instability doesn't work anymore, that you actually need a finite interaction in order to get any delta in this, because it's called quantum critical point. I will show in a moment how large this interaction needs to be, but basically there is a specific value for it. On the other hand, if you consider this case of flat band, which is kind of the opposite of Dirac point, you get anomalous, very large delta, which relates, delta is actually linearly proportional to this coupling constant times then the area of the flat band. So it's linear in G, and presumably you should get much larger delta in this case. So these are kind of the extreme limits. In practice, of course, you need to take into account the details of the dispersion and study what happens. This is what we have done, but to get you some idea what different limits which would correspond to.
Tero, I have a question. So,
yes.
Concerning the last discussion, how do you go in? I mean, you mentioned that you can achieve the flat band limit by reducing the velocity, which is what they do in twisted graphene. But so, how do you interpolate between these two limits? The graphene case, where you need to have finite
Yeah.
Interaction strength to the flat band limit?
Yeah.
You're reducing the velocity.
Excellent question. Actually, I will show a picture about this, but sort of a hint to this picture is that the critical coupling strength depends on the speed. So if you reduce the speed, the GC becomes actually smaller.
Yes.
So and this way you actually can interpolate between the two cases.
So if you reduce the coupling to 0, would you get? I don't see. Would you get a linear display? Because it seems that
you reduce BF to 0, indeed you get linear from here. So if you take GZ to 0, then delta goes like G. Right.
Okay.
Yeah, there are other things, of course, but this is just a mean-field solution of these equations, how they go. But that was a good question. Yeah. Okay, so this was kind of the instantaneous interaction where you just assume that there is some attractive interaction. You can also do the Eliashberg sort of properly for these flat bands, in which case you kind of consider the electron-phonon coupling and you assume that you get a self-consistency equation from the electron-phonon self-energy, and this sort of approach also allows you to include direct Coulomb interactions via this so-called Anderson model pseudopotential trick. And I have some slides to show if there are some questions, but otherwise I just give you the conclusion of this consideration. Basically, one thing is that you need to take into account the screened Coulomb interaction here, including retardation effects. And such a screened Coulomb interaction is kind of then described by effectively a coupling constant U, which is kind of a repulsive interaction. And then the electron-phonon is described by a coupling constant lambda. And once you put these together, the effective BCS interaction will depend on the difference of these lambda and U. And if G is now positive, then you get the superconducting state. That's kind of the hand-waving way to quickly go through this, but sort of doing this first line here involves a bit of work. But the bottom line here is actually that the screening itself can be a sample sort of dependent thing, not only materials dependent thing, and therefore actually superconductivity in this sense might not be materials dependent, but actually sample dependent, especially in 2D cases. Okay, so once you do this Eliashberg, what you get in the this Fermi surface case is this Macmillan Allen Dines formula, Macmillan formula, I guess it's called, where the TC is now sort of basically this exponentially suppressed TC, but there are some corrections from the so-called pseudopotential terms, and there are also higher order terms in lambda. These are based on so-called Miguel's theorem, which states that for dBi frequency small compared to the Fermi energy, you can go to higher order sort of effects in lambda, but still do self-consistent Born approximation in the electron-phonon. This actually fails for flat bands. I will discuss it in a moment. You can do the same for flat bands and you get this linear dispersion, but once you include the Coulomb at large lambda, you also get some corrections. But now these corrections actually rely on this sort of self-consistent Born approximation only, which might not be valid anymore for large lambda. But the bottom line is that for small lambda, you get this linear dependence on lambda. And yes. Okay, now we want to describe graphene. So we can ask, well, how large would be an electron-phonon coupling that sort of you would get from, let's say, the attractive interaction that you would get from electron-phonon coupling. And there have been a few estimates in the literature. Actually, in all these papers, there is one same author, which is Feng-Ching Wu, but the papers contain different sort of sizes of the coupling constant. I show this here to kind of show that this thing exists, and you can estimate it based on sort of quantifiable sort of things like deformation potential, mass density, speed of sound. And the second thing that I want to point out that this coupling constant actually has a dimension of energy times area, which means that any sort of calculation that you do requires, if you want to go from the coupling constant to critical temperature, you need to have something that contains area. Okay. Yes. So these are the kind of upper estimates of this coupling constant. The true coupling is smaller because of Coulomb interaction. But let's take these values and see sort of what would happen in a monolayer graphene. And in monolayer graphene, this critical interaction constant is 7 electron volts times nanometer squared. So it is much larger than these G values, which means that at Dirac point, you are much below this critical point for superconductivity. And therefore, at least at Dirac point, graphenes would not become superconducting. But then you can assume that you dope the graphene and then you try to get it superconducting. And just sort of making estimates of how large doping you would need to get delta, which has a size of equivalent to 1 Kelvin. The TC would be then a bit less. If you assume this smaller coupling value, you would basically require doping, which is almost the size of the conduction band in graphene. So this is not that easy to realize. So this basically states that monolayer graphene is not a superconductor, at least not very easily, which is something that was kind of known in the literature already before. Okay, now I have discussed the fact that I want to discuss superconductivity on a flat band, and one thing is, of course, to consider this mean field gap. But can the electrons on such flat band actually give rise to superconductivity? Superconductivity does not only require that the gap is finite, but also that there is a finite superfluid weight. This ds here, which is the prefactor between the supercurrent and the phase gradient. In the conventional BCS theory, the superfluid weight is proportional to the particle density divided by the effective mass. And this effective mass actually diverges for a flat band, which means that let's say the Cooper pairs in this case would sort of be completely localized, and they couldn't carry any current. But in fact, this conventional BCS fails for systems which have extra degrees of freedom in the unit cell. It's because you may get also other components. And and this is the case of multiple bands in the system, in which case this superfluid weight contains the conventional one, which is basically proportional to the inverse mass. But then there's also a geometric contribution that depends on the kind of one-year function structure of the eigenfunctions of the on the Fermi surface, Bloch eigenfunctions, and basically this T is finite if the one-year functions are non-localized and overlapping. And okay, and actually, sort of this geometric part of this superfluid weight was shown by Piotta and Törmä to be sort of contributing to the supercurrent, but also this is the same thing that is sort of related with the geometric properties of the Bloch eigenfunctions and so-called quantum geometric tensor. I will not go to detail of this here too much, but basically the point is that from this quantum geometric tensor you can calculate, for example, Chern numbers. And if you have a finite Chern number for your system, then there is actually a lower limit for the superfluid weight in these systems, so that you can have a flat band, completely flat band, and still you would have a finite superfluid weight. Yeah, in this case, the only thing that you need to consider beyond mean field is basically that if you have a 2D superconductor, the transition to the superconducting state is not described by the mean field theory, but actually it's described by the Brzezinski-Kostelis-Taules transition, where the sort of vortices kind of they become trapped below this PKT temperature. And in practice, this means that there may be kind of a zero gap phase where between the PKT temperature and the mean field TC, where there is a gap but no supercurrent, no real zero resistance. I mean, and it's actually this PKT temperature that has been measured in the experiments. Now, this is the theory that we want to do, and there are sort of possible some caveats on this theory. So that mean field theory might not be valid. So it is probably okay for let's say the zero temperature limit when you don't have to include these phase fluctuations. Once you include the phase fluctuations, indeed you get this PKT transition. But actually, there's also the possibility of amplitude fluctuations, which is basically the Higgs mode that affects, let's say, the dynamics. And this is another way to kill the mean field. If you're interested, I can talk a bit more about how we have estimated these amplitude fluctuations in the rhombohedral graphite. But I just mentioned this, that these are usually described by the so-called Ginzburg number, which is a sort of proportional to the ratio between the critical temperature and Fermi energy, and in the flat band case, Fermi energy becomes small, so this can be of the order of unity. Okay, and then another caveat is this failure of the Miguel theorem, which basically states that you can do the self-consistent Born approximation for electron phonon, but actually for low order, in the lowest order, this is okay. And yeah, and another caveat is that I only consider the superconducting state, but actually there could be also other types of correlated states, which is what has been seen in twisted bilayer graphene. Yeah, so what we do here is that kind of do this PKT transition, but we start from the mean field and we calculate the superfluid weight in the mean field. There are also some kind of completely beyond mean field works which have studied this flat band superconductivity, and but I would say that typically their results agree quite well with the mean field results that contain this PKT physics. Okay, so let's go to this graphene superconductivity observations experiments, and I will describe these three, and in the coffee break, if you wish, I can describe some theory for the fourth one. So I will start with stacked graphene, and then I go to twisted bilayer graphene, and then this periodically strained graphene actually goes to the coffee break. For the, I guess, for the lack of time mostly. So we start from the graphene. I already showed this picture. So where you have this pair of Dirac points. And now we want to stack graphene. Actually, we want to make graphite from it. Interestingly, nowadays, people know much better the electronic spectra of graphene than graphite, although graphite has been known for centuries. But okay, how you get there is that you want to stack graphene layers, and the way how you stack every pair of layers is this so-called Bernal stacking, where you take the two layers and then you shift, so that let's say the graphene lattice consists of this blue and red atoms, meaning just that the unit cell contains two carbon atoms. So in the other layer, the blue atom goes on top of the hexagon, and the red atom goes on top of the blue atoms of the previous layer. This is the so-called Bernal stacking, which is the most stable one. And if you do this and you study the bilayer case, you get this quadratic dispersion in a certain approximation, and then let's say the higher order terms that you might also sort of include from higher order hoppings, they slightly deform this spectrum close to zero energy. Now, if you want to go from this sort of bilayer to a higher number of layers, you have to make a choice. Either you do the so-called Bernal stacking, which is called also AB stacking, or you do the rhomboidal stacking, which is called ABC stacking. And the electronic spectra in these two cases look slightly different. In fact, both of them are nodal line semimetals. Bernal stacked one contains actually lines which go mostly straight, whereas the rhomboidal one contains spiral lines. I will here only concentrate on rhomboidal one. But so that you get some idea of what happens to the spectrum if you only consider the strongest coupling sort of between the layers, which is basically the one, this kind of gamma one, which is the one which is connecting these sort of atoms on top of each other. Yeah, and then sort of one way to picture this system is that we have lots of graphene layers where the red and blue atoms are now the A and B sides of the individual unit cells, and basically they are coupled at finite momentum due to the sigma dot p Hamiltonian of graphene. And now once you start sort of including the interlayer coupling, you couple blue to red, but not red to blue. Okay, and this way, so you can create either this rhomboidal stacking or Bernal stacking, depending on. So in the Bernal stacking, this coupling is a zigzag. In the rhomboidal one, it's goes like always in the same direction. So yeah, and now let's see. Okay, let's consider this rhomboidal multilayer only that has a flat band on the surfaces. What you find out is that at sort of p equal to 0 at the Dirac point, there are two uncoupled sides. This blue one here on the top and the red one on the bottom, and they actually are sort of localized sides at p equal to 0. And once you put the finite momentum away from the Dirac point, then you induce some non-localization for these systems. And actually, it's the overlap energy between these two eigenstates that provides a finite dispersion in this system. And this gives basically the speed at the nth dispersion here. And in the limit of large n, you have this flat band in the spectrum. So this is the energy as a function of px and py around the Dirac point. Now, the reason why you get the flat band is actually quite somewhat interesting. So I just quickly explain it. So you can actually write the Hamiltonian of bulk rhomboidal graphite, which is also a 2x2 Hamiltonian, and then this gamma 1 term comes here. And what you find out is that in this case there is a spiral, so that there's a band touching at sort of given perpendicular momenta equal to something that depends on this sort of pz, and in particular there are these spiral states, and this is a nodal line semimetal, which means that at every sort of point on the spiral you have a nodal this kind of Dirac point touching, and such nodal lines have actually a topological charge. So if you look at then what happens at the surface, you have a projection of these nodal lines on the surface, which projection then actually describes this flat band. So this is the zero energy state due to the topological bulk boundary correspondence of these nodal lines. So here they are called flat, but actually if you, yeah, okay, I will come in the moment what happens once you include higher order hoppings. But now you can then basically plug in the attractive interaction and consider the superconducting state in this system. So the exact details will depend on the size of this coupling that you include. But the kind of the bottom line is that you get this surface superconductivity. The delta becomes finite at the surface for sort of coupling that is not too strong, and then there is some decay that depends on the exact size of the coupling. And you can study, of course, also how this sort of delta depends on the finite n. There's actually a pseudo-analytic formula for this delta, but for very large n, you get this limit where delta is linearly proportional to the coupling strength. And in this case, it's actually from this delta you get a critical temperature by putting a factor of 3. So this is not the same factor as in usual BCS theory for Fermi surfaces. And also you find that the doping destroys this surface superconductivity at the sort of doping level that depends on delta. Yeah, you can also consider this sort of, this was based on kind of only taking into account this gamma 1 hopping, but you can also consider what happens if you have higher order hoppings. And one thing that sort of they do is that they break a certain chiral symmetry of the Hamiltonian. And it's actually this chiral symmetry that protects this flat band, but even without this chiral symmetry, you still have a surface states, but now they are so-called Bramhead states. So there is some finite dispersion on the surfaces of these states. It's actually there's a quadratic dispersion which is characterized by a bandwidth which is this alpha, which depends on this parameter gamma 4. And we estimated that this alpha has a certain magnitude that you can estimate. Basically, the statement is that the mean field TC, if it's larger than 20 Kelvin, then we are completely in the flat band regime. If it's of the order of a bit less than 20 Kelvin, you have to still sort of, you cannot do a Fermi surface approximation. You have to go much below that in any case. And okay, you can make estimates with this sort of coupling strength values that I gave earlier. And basically, if you take the larger coupling, you get actually TC, which is almost 30 Kelvin. If you take the smaller coupling that was provided in the literature, you get maybe 4 Kelvin. So sort of, and we probably are rather here than here. So now that we know the sizes of the couplings pretty well, we can estimate this sort of rhomboidal graphite should have a few Kelvin TC. If you take a smaller number of layers, like 3, you are expected to get a smaller TC. And this is actually what happened. So this is the experiment that was published. Yeah, actually, this is already now in Nature. This was in Nature this September, so I should have actually added the reference. I think it was in my earlier slide. So basically what they did here was to take this rhomboidal 3-layer graphene, and they studied the resistance as a function of the charge density and as a function of sort of chemical potential difference between the layers, which is basically an electric field inside the graphene. And then what they find is these superconducting lobes. So this SC1, and then there's another one here where there is a zero resistance state for sort of below some critical temperature. The largest critical temperature that they see is actually around 100 millikelvin. So smaller than this 4 Kelvin, but sort of this is most likely due to the fact that there are only 3 layers. Yeah, and the SC2 is somewhat interesting because they also studied what happens in the presence of magnetic field. This is not shown here, but what they showed was that actually the in-plane magnetic field does not kill superconductivity here, and so they claim that maybe it's triplet order parameter. But basically, these lobes here that you see here are actually consistent with the fact that we are changing only the potential of the let's say top surface here, and not sort of once you fix the potential of the top surface, which is kind of, this is the equipotential line, nothing changes almost, but it only changes in this direction. So this is consistent with what I described earlier. And also there is actually a direct prediction that if you would go to a higher number of layers, you would increase the TC in this case. Actually, Dasarma and others, they took our approach and they applied it for this three-layer case, including all the sort of hoppings and also this electric field, and they basically find something that is on the order of this 100 millikelvin. They don't study PKT temperature transition, only the mean field TC. There's another experiment, very recent, on now bilayer graphene. So bilayer graphene was studied already in the early days of graphene quite a bit. Those who were there may remember the fact that the bilayer was used to prepare field effect transistors from graphene, because the kind of what was told that the graphene's problem is the fact that there is no gap. So it is hard to make logic elements because the resistance is always finite and not, or let's say conductance is always finite. But with bilayer graphene, people managed to make gaps by applying this electric field inside, and this is what actually happens in the system. So you have different Ds here, and you have the bilayer spectrum. So starting from this quadratic touching, you go to this gapped phase. And to make the story short, they find superconductivity once they go to these edge states. And actually, Dasarma also there use a similar approach as ours to show that sort of the electron phonon is also can be sort of in charge of this. I mean, can explain these experiments. The curious thing about these experiments was the fact that the superconducting state, which is actually here, only shows up at finite magnetic in-plane magnetic fields. At zero fields, it doesn't show up. Okay, I realize that I have used already a lot of time, so I just mentioned that. So the one way to kind of get these flat bands not on the top or bottom surface would be also to make so-called twin boundaries where the stacking changes along the way, so that you would have also these localized states here, and in this case, actually, the delta would become also finite inside this twinning boundary. And I should mention this experiment. This is already from 8 years old, from Pablo Esquinaz's group in Leipzig, where they took highly oriented periodic graphite, and where they knew that there were internal interfaces. They actually are between different orientations of the graphenes, and they found out that sort of systems that contain these interfaces had a superconducting transition, or at least a transition to a zero resistance state at very high temperature. So it could be, or maybe could not be explained by this sort of twinning boundary mechanism. The problem is that we don't really know what is going on in those experiments, what happens in the structure. And there are very large sample-to-sample variations. Okay, I try to spend a few minutes on the twisted bilayer graphene. So the idea is basically that you take two graphene layers and now you stack on top of them, but then now you twist them with respect to each other, and you get this moire superlattice. And let me cut the details a bit. Basically, at a certain magic angle of twisting, you get a flat band. And this flat band was known already sort of since more than 10 years. And then the superconductivity is kind of more recent. Let me go to those superconductivity observations, and this is what Harilo Herrero showed 3 years ago, and now also many others, but this was the first experiment. They find, as a function of the charge density, they find these superconducting states, which now have, in this experiment, there's a TC of 0.4 Kelvin, but people have gone up to 2 or 3 Kelvin in TC. And basically what we wanted to explain these experiments, actually we had worked on this much before the experiments, but once they came, we wanted to explain them by doing the mean field here with different types of pairing schemes, and sort of find in this system a mean field order parameter which is strongly localized, so it contains this kind of lobes of finite delta. Depends a bit on how large a coupling strength you put, how large this delta is naturally. And here is basically the picture of the delta versus coupling strength in this twisted bilayer graphene. There's a critical value of coupling, and then beyond this critical value, you get a linear dispersion, a linear scaling. And okay, now you can also sort of, in this case, estimate the size of this delta versus lambda. And okay, what we also did was to do this Brzezinski-Kostelis-Thouless physics and study it as a function of different parameters, including the angle. And here is actually a comparison of our results to experimental values of PKT temperatures as a function of angle from two experiments, and they seem to match pretty well to this sort of lambda being this 2 electron volts times a squared, where a is the graphene lattice constant, and now from here we can then estimate so how large would be the delta in this system, because this is not directly accessed in the experiments. And it would be of the order of 2 milli-electron volts, which would correspond actually to a somewhat higher mean field critical temperature. The BKT temperature is smaller, and actually then comparing the different contributions to the superfluid weight. This is a picture of the superfluid weight contributions depending on delta. At small delta, it's mostly this conventional contribution. At larger delta, it's this geometric contribution. We find out that already this geometric was very sizable in these experiments.
Tero, you have about 2 minutes left.
Yeah, I will. I'm basically almost at the end of the talk. So I try to make a kind of a conclusion of this sort of studies. Flatband superconductivity requires that this flatband delta is large compared to the bandwidth. In the case of ABC graphite, this was definitely not the ABC graphene. This was definitely not the case. In the case of twisted bilayer graphene, it's actually a borderline case. The delta is of the order of the bandwidth, which means that you already need to consider the full band. Actually, you cannot do firm surface physics. And but one thing that you learn in the flatband limit is that the delta actually is proportional to the size area of the flatband in momentum space. And in the case of twisted bilayer graphene, this area actually corresponds to the area of the Brillouin zone of the superlattice, which means that in that case, actually the area is much smaller than the original Brillouin zone sort of area. It's actually by a factor of 10,000 smaller than that. But still you get the PKT temperature of the order of a few Kelvin. So the message here is that to increase the DC in these systems, you should look for systems that have a larger Brillouin zone, or larger flatband area. This was actually done in one experiment where they applied pressure on this bilayer graphene, and this way they could find the this magic angle at higher angle, flatband at much higher magic angle, which actually led to a larger DC. So this is kind of consistent with this picture. There's also sort of their way that to study what happened, sort of what is the sort of origin of this other states, except for the superconducting states. I can discuss it if you wish, but I will probably skip it here to keep the time. And rather, actually, I come to the conclusions. So the what I am now claiming is that there are now several experiments on sort of superconductivity in graphene-based systems. So twisted bilayer graphene, this rhomboidal three-layer graphene, vernal bilayer graphene. There are also some experiments on the strained graphene. And my claim is that superconductivity in all these systems can be understood with electron phonon mechanism. But in order to understand it kind of quantitatively, you need to include the contribution from the whole flat band instead of just the firm surface. So the nature of superconductivity in that sense is somewhat unconventional. And in this case, actually, the TC is proportional to the area of the flat band. And in order to increase the TC, we would like to increase the flat band area in some ways. And during the coffee break, I discuss one mechanism how to do this, if you are interested in that. So I stop here and thank you for your attention.
Thank you, Tero, for a very interesting talk. So now we have some time for questions. I mean, feel free to unmute yourselves and ask questions.
Hello, Tero. Can I ask you a question?
Absolutely.
Yeah, just a naive question. So this flat band, let's say, it depends on the strength of the interaction, let's say, if I understand well. So
no, the flat band doesn't depend on the strength of the interaction.
So if we start from the band insulator, if I take a surface, make the defects,
yeah,
if they are well separated, I have just a level.
Okay.
Then if I increase the density of these defects, they start to interact and the band appears, it starts to disperse, but it will be very, very flat. If I increase the concentration of these defects, it becomes more and more, let's say, dispersive. Does it work this way, or?
Yes and no. So most likely in this case, you may have a finite delta, let's say, in my picture, but 0 d. So even though you would create some BCS pairs from attractive interaction, you would not have any, the critical current would be 0.
Do you know the results of the, I think that was reported as superconductivity on the interface between two insulators?
Maybe, yeah.
STO, LS.
Yeah, this oxide interface. Yeah. I cannot comment on whether this is relevant mechanism there. Yeah, I guess the main point here is that let's say in these systems you cannot use the usual Fermi surface sort of arguments in estimating anything, because you have to take into account the full band. But however, the mean field theory seems to sort of provide a pretty good description of the sort of at least the overall size of the effects.
If I take a 2D material and make a periodic array of defects in the topmost surface, will it work?
In principle, yes. This is actually the point of this sort of periodically strained graphene.
Okay.
Yeah.
Okay, any other questions?
I have a question. So in principle, everything you obtain is isotropic in momentum, because you are just relying on the low energy dispersion of the cone.
It's a good question. So you mean that do I get always S-wave?
No, I mean there are other reports, for example, by the group of Annika Black-Scheffer, where they claim that you have a nematic effect or anisotropy. Can you go beyond your, let's say, S-wave coupling?
Yes, and we did this in the case of this biographine. Let me see. I think I'm probably, where is it? In fact, here, yeah, so here's an example that actually we considered two types of pairing interactions. Here, one that is completely local pairing, and then one that contains nearest neighbor, a lot of attractive interaction, so-called resonant valence band pairing. It's just a sort of effective model you get basically finite superfluid weight in both cases. The details are somewhat different. One of the interesting cases is indeed that with this resonant valence band, resonating, what is it called? Well, this RVB sort of interaction, you get a nematic state beyond some critical coupling value. And I think we are beyond this value. And the nematic state in this case shows up actually in the way that this superfluid weight actually is anisotropic. So it is a matrix. Actually, you apply a phase gradient in one direction and you get a finite supercurrent also in the perpendicular direction. And this would be a way to measure this nematicity actually.
Can I make a second question, Miguel?
Sure.
So, and I assume that in you're always assuming that all the layers of your system, multi-layer system, are always perfectly flat without any buckling.
Well, this is.
But if you take okay, the point is that in order to get this physics of Bicester and McDonald from in a tight binding model, you need to add. Sorry, to get this, to get something in the effective model in the DFT, you need to add the buckling of the graphene surface. So the atoms are not always to the same distance from each other on the two layers. While somehow I assume that your Bernal stacking or rhomboidal stacking is assuming perfect flat layers. Am I correct?
Well, it depends on which model you are referring to, because in fact the twisted bilayer graphene theory that we do here is based on unit cell that is very large unit cell. So okay. We are sort of we are assuming the business McDonald model is assuming just a single parameter sort of coupling between these twisted layers. But we don't use that one. We use a model where we parameterize the sort of coupling between the atoms, and in terms of the distance and the direction of the coupling. We find the nearest neighbor couplings in the unit cell, and then we kind of take the full coupling matrix. Okay. It took a couple of years for my students to manage it, but I mean, we have published these mathematical codes for calculating this. So, but yeah, it's a complicated thing. We don't take it there into account the buckling.
I see.
So I'm not sure how relevant it is. The magic angle that we get is very close to what they see in the experiments.
I see.
So at least it's not too bad in that sense.
Okay, thank you.
Yeah, welcome.
Okay. I think before closing, I would like to ask a question, because I think you mentioned at some point that the delta could have some momentum dependence, but of course the order parameter can also have some non-trivial spin dependence, and this is connected to some experiments where, I mean, in plane magnetic fields and so on. So whether it's P wave or
for example,
and so on. So am I correct if I understand that you're assuming that the order parameter is wave all the time in this spin?
Yes. So what we do is that we assume this local interaction, and then the estimates for the size of this local interaction from electron phonon coupling are based on just kind of projecting to the local one. But for example, Dasarma in this paper and also earlier Fengchen Wu for twisted bilayer graphene, they show that electron phonon actually can lead to twisted bilayer graphene can lead to a D-wave state, but it's actually subdominant in the sense that it has a higher energy than S-wave state. And in this case, what Dasarma they show that actually both the S-wave singlet S wave state and the triplet F wave states actually are degenerate without in the zero magnetic field, and then at finite spin splitting field you favor the F wave triplet. Right.
Yeah, because the spin structure of the superconducting of the parameter can also modify the BKT transition in the sense that, I mean, it's no longer a scalar, so you don't have vortices. You can have more complex kind of you know, spin structures and stuff like that. I mean, half vortices and stuff. So
you're right. Yes, that's a very complicated issue. And here I sort of what actually the Sarma's group is doing is already only the mean field. So our BKT.
What you call BKT, TBKT in your talk was essentially the mean field. Essentially
No. Okay, so one has to separate experiment from theory. So in experiments they measure the BKT temperature. So
sure. So what they computed is what is the
what we calculated. I mean, we have calculated both the mean field TC, but also in the case of twisted bilayer graphene, we also calculate the BKT. So this is let's say here everything is mean field, but then we go we use the mean field to calculate the superfluid weight.
Yes.
Then from the superfluid weight we can calculate the BKT temperature. So
that assumes that essentially the other parameters is wave, because you are going to use the kind of like Costa-List Nelson whatever relationship, right? So but if it's not standard BKT thing, then it's more complicated.
I guess so. Yeah,
it's not that equation.
Yeah, it's actually this was not a simple calculation, because you know this is calculating superfluid weight in the case of this 10,000 sort of atom unit cell.
Yes.
For as a function of different parameters, and you are right, most likely one should go even beyond that for twisted bilayer graphene. So this three-layer graphene and the Bernal sort of bilayer, they are much simpler in this sense.
Okay, so maybe I stop recording here, and we can go to the